And so these are considered out of distribution. And what that means is the model didn't see enough of this kind of data to be able to recognize it.
Welcome to Practical AI, everybody. My name's Jeff. I'm with Peter Lynn. We are in our second season of Practical AI, and we are doing a series. This is episode 2 of how to train your own model. We are sponsored by poqet AI. poqet AI is a tool used to perform surgery on your models to make them better. While everyone today is talking about RAG and refinement, poqet AI allows you to edit the weights in your model directly. Peter, a pretty common topic out there that we haven't discussed much, but it's in the literature, is similarity in large language models. And we wanted to kind of tap into that and a concept that you've been talking about a little bit, and that is generalization scores. So can you tell us a little bit about similarity and generalization scores?
Yeah, so it's an old topic of when you are training a model, everyone's goal is to create a data set that is as diverse, in big air quotes, as possible. Obviously, you can't make a data set that is infinitely diverse because that would mean infinite amount of data. And everyone that builds data sets has to make that judgment of like, okay, what do I actually need and can I actually get it? But then the question comes up of like, well, if I have 4 pictures of a Siamese cat, is that different enough? It is just taking a profile, left side, right side, and back of a Siamese cat different enough to really give you a good result, or do you need more diversity of data? And so this just goes back to the idea of similar. And humans have this bias of like, well, I think this is similar, but a model considers things similar in a completely different way. And so I'm going to share my screen. All right. In poqet AI, after you've done your training, what you can do is you can use the Python scripts that we provided for free to generate a report for your test data. And all it does is this is right. I'm going to go through my data. I'm going to run it for every version of the model in the training. And if they got it correct, it's a 1. If they got it wrong, it's a 0. And from that, we can easily calculate a score, which we call the generalization score. So why is this useful? Well, it's useful because if we want to see all the data that had a certain accuracy, we can easily filter that and we can sort it. So for example, if we want to see all the images that were correct fairly quickly, we can find all those pretty easily. If we want to see the opposite, we can look at all the pieces of data that had never got correct. And so these are considered out of distribution. And what that means is the model didn't see enough of this kind of data to be able to recognize it. And so the first step is we can filter the data based on the score. And then once we've done that, we can actually then look at the actual. So let me just scroll through a couple here. All right. Let's see. So for example, if we go to ones that scored 0.075, we can look at which epochs failed, and we can look for similar patterns. And the reason why this is useful is the chances of 2 pieces of data having the same exact failure pattern is kind of unlikely. And this is a good way for us to then compare the training data set and the test data set. And once you know that, you can then adjust the distribution for data so that maybe instead of 80% of images always get it correct, we can maybe split it to like 40% of those images are used, and then we add more data that has a hard time on. And then this way, we're building a better data set that in theory and in practice should give us a better result.
So if that's true, then you could essentially train your model much more accurately without having to grow the data set considerably. You would just have to change the data set in terms of maybe the percentage of things that it has a hard time with.
Exactly. Yeah. So like today, because no one is doing this kind of analysis, everyone just adds more data, which that's one method, but then you don't know when you need to stop. And then you also don't know if adding that additional data ends up skewing your data set so that you get other bad results. At the end of the day, you really want to know, like, okay, what parts of my data is good and what parts of my data is causing my model to behave in ways that I don't want.
So it makes sense that you would try to find more of the errors or the out of distributions so that you could skew your training data set. What I was curious when you said that looking for patterns on which epochs, explain how that is helpful when you are trying to leverage the generalization score in terms of training for a more accurate model.
Yeah. So let's just go to, let's see. I'm going to go to some that maybe scored. Okay. So let's go to scores that are 0.275. Right. So if we compare just these two here, 0.1273, and the one right beneath it, we can kind of see, okay, well, so this top one here, first failure was about 12 or 13th in, and the other one also was similar. But if we actually look at the pattern of like failures in inaccuracy, we can start to see which ones the model considers similar, because today the way that the literature recommends is you train a second model to figure out whether two images are similar, but then that creates another problem. Now you have to train a second model to figure out what your model considers similar, but that's a separate model from your actual model. And so now you got two problems. Is this other model actually giving you the correct similarity score? And is that close enough to your actual model that it actually improves your real model? And so it doesn't act in practice, training a separate model to figure out are these images similar actually doesn't really work.
So you've got computer vision model here. How would this work with a LLM?
So with LLM, similar thing. So let's just take the simple case of like, let's say we want a math model and we give it 1,000 math problems. So I mean, the answer is either right or wrong, right? Um, and so we can do the same thing where we feed the test data and the training data and we compare the two and we go, okay, here's the failures in the test data set. Let's compare it to the training data set. And then we can then adjust the training data so that, okay, so let's say we've got a complex calculation with multiple parentheses, right? Well, what you could do then is you can then just look at those examples and you could make variations of those. So maybe you have like two parentheses that have a multiply, and then you add the result of those two parens. Well, then you can you know the formula now. You can generate more examples like that.
And then with computer vision, images are either right or the wrong, math problems right or wrong, code that's more likely to be right or wrong. Eventually you get into something that's a little bit more subjective. So let's just say something totally subjective. Write me a poem in, like Thoreau or something like that.
Yeah.
So would you be able to apply similar, would you be way more into just classic similarity at that point, or can you still do something similar from a generalization score?
So you could use cosine similarity, which is what everyone uses for large language models today. And that's just basically taking your prompt, tokenizing it, storing the tokens as a vector in a vector database, and then calculating the similarity. So you could do that. But so using this approach, you don't have to give it a 0 or 1. You can have a human. So this is the reinforcement learning with human feedback part, where you could have a human go in, look at the results, and give it a score. So maybe you think it's, it was half right. It was kind of okay, the response from the prompt. And so then you can go through and give it a score of like 0.8 or 0.5. And then you could still go through and calculate the score in order to filter and figure out like, okay, what do we need more of? What do we need less of?
Okay, so that at that point, you're kind of getting into weighting, and just by weighting it, you could use a generalization score method and get there.
Yeah.
Great stuff, Peter. Very helpful. I think next week we're gonna hit up accuracy and loss. Will be our next topic. So we hope everyone will join us. If you have any questions, you can always ask. We would be happy to answer them, and just leave any notes in the YouTube comments. Take care, everybody.